So, maybe I will now start talking about maxima and minima, and many people might be wondering that I am wearing the same dress. Actually, these lectures are usually recorded in a continuum for some 2-3 lectures, and which obviously each are separate lectures, but they are done in the same sitting in some sense. So, teaching is somewhat in some cases is been in the show business, and I am trying to convince you about things. So, everybody knows about maximum and minimum, these terms are very common. Common not only in as a mathematical term, but common as a term that we use in a daily language. In fact, I know of a family in Delhi which has 2 daughters, one is named Maxima and other is named Minima. It is very interesting for me because this is a part of mathematics which I have dedicated my life to, and so it is good to speak about this. So, what I mean, I have already told you what is the maximum value of a function and minimum value of a function. So, I can repeat the same thing once again just to recall you. So, suppose f, I am first looking at this situation, f is a function from R to R, and A is a subset of R. So, here I have given this equal to sign at the bottom to show that A could also be R. A is a subset of R and X is called a minimum, or sometimes people also call it a minimizer. So, there are various ways. Spivak they call it minimum because if I go to the real domain of this maximum and minimum called optimization in a joint form, if I go to the domain of optimization theory, I would really start calling it as a minimizer. So, there are several ways mathematicians like to call this point, but let us call it a minimum because in calculus they will call it a minimum. X is called a minimum over A if f of y is greater than equal to f of x for all y in A. So, A could be a open interval, a closed interval, a union of open intervals, it could be disconnected open intervals, disconnected closed intervals, anything. And it just it does not mean that A has to be some very specific set of very specific nature. This is the general definition of a minimum, and I would really ask you to find the maximum, define the maximum. There is another definition of, say if I take from R to R and A is a subset of R. So, this minimum that I have defined is often called the global minimum or global minimizer, and the functional value at f is called the global minimum value. For a usual optimization theorist, they would call x to be the global minimizer and f value to be the global minimum. So, x in this case is called the global minimum. So, now there is something called a local minimum. So, let us look at the picture of what I am trying to say. So, suppose I have a function defined say from this point say A, and ends in B. Now, if you look at this point and this point, you can understand that this point is the lowest, has the lowest function value. Among all values, this point has the lowest functional value. But this point, which I have another point which I have marked at this point, the function at this, so at this point, this is x and say this is x dash. At x dash, the functional value is bigger than the functional value at x, but for some region of the set AB, the closed interval AB, the functional value at x dash is less than all other values in that very specific zone, say in this zone. So, it is a minimum, but not in the over the whole interval AB, but over a very specific region of AB, a subset of AB. So, such things are called local minimum, and we will make it more formal. Okay. X is called local minimum of f over A if there exists delta greater than 0 such that for all y which is element of A intersection x minus delta x plus delta. So, this is intersection f of y is bigger than f of x. Now, let me mention two important facts about optimization problem. So, if A is equal to R, then we say that the problem is unconstrained, there is no restrictions on the problem. If A is a proper subset of R, then we call the problem to be constrained. So, now, our first study would be that of the unconstrained optimization or minimization problem. Maximization and minimization problems are absolutely ubiquitous to mathematics and to many sciences, into physics, to chemistry, to biology, to many everywhere. Optimization, to engineering, to business, optimization plays a very central role. Now, here my problem is simply stated as minimize the function f, or if you want to be more precise with the function values, with x over R real line. So, what can we say about the nature of a minimizer? How do I compute a minimizer? So, my first step is how do I compute a minimizer? Or compute a minimum point. Of course, there is no guarantee that a minimum value would exist on R, because R is not a compact set even if the function f is continuous. So, let us be more naive and think that okay, x star be a local minimizer of f, right, then over the whole R, then how do I actually start computing such a point? And to do so, you need at your basic level some more additional information, and that information is that of differentiability. So, now we will consider only functions from R to R which are differentiable. We will not discuss any function which has points where the function is not differentiable. So, if x star is local minimizer, what can we say about x star? Does it satisfy any condition? So, if x star is the local minimizer, is there a condition which it must necessarily satisfy? If it satisfies a particular condition always whenever it is a local minimizer, then we can use that condition to compute an x, which we can then test whether it is a minimizer or not. So, there are two aspects of this computation of a minimum. One is the necessary part and one is the sufficient part. So, we will put this bordering wall between the two. So, if x star is a local minimizer, then this condition always hold that the derivative at x star would be 0, because we are only considering differentiable functions. So, suppose this is a local minimizer. So, x star is your point. Then take any other point nearby, say x star plus h, where h is positive basically moving on the right direction. So, you look at the slope of this secant, this angle is acute. So, the tangent value is greater than or equal to 0. But if you make h say negative and if you come to this point say x star plus h1 where h1 is negative, then you look at the slope of this secant, here the angle is obtuse, so the slope is negative. So, if you say the key fact about this point a local minimizer is that, so within some domain, within some delta neighborhood, if you keep on moving x to the moving if you keep on moving towards the right from x star, the slope of the seconds will remain positive, while if you move to the left the slope of the seconds will continue to remain negative, and that is the key, negative or 0 whatever, that is the key idea behind the fact. So, basically the derivative, if I think of it as a continuous function which is continuously varying, the slope is continuously varying, so it moves from positive to negative. So, there must be a point where it must be 0 and that x star is the point where it is 0, that is the key idea. This is a geometrical idea, but let us just do it. So, what happens that if h is positive and small, and that is within a given neighborhood. So, that is the meaning. So, f of a plus h, sorry x star plus h, f of x star plus h minus f of x star is greater than or equal to 0. Now, if I divide by h, because h is positive. Now, if you take the limit as h tends to 0, as tends to 0 plus, because the derivative exists, it does not matter which limit you take, it will always, you will get the derivative. So, you will get f dash x star is greater than or equal to 0. But now if h is negative, if h is negative, so here this would remain same, but when you divide by h, this inequality will change. So, you will take the limit as h tends to 0 to prove that, and when you combine these two, you will get that f dash x equal to 0. So, if you combine these two to get f dash x star is equal to 0. I ask you to prove another result at home. Let f is now defined. So, here I am optimizing over a subset. So, it is a constant optimization problem, but the set A is an open interval and f is differentiable and x star is a local minima. So, I am using this word h, is small, means it is the local minima, it should stay within some given neighborhood, delta neighborhood. So, because if A is equal to R, then y should just belong to x minus delta to x plus delta. So, the intersection would be just this. So, and x star is the local mean, then f star x star is equal to 0. If I make this to be a closed interval, this result will not continue to remain true. So, whatever I have on R, I will have the same story on the open interval as far as the necessary condition goes, but it will not be the same story over it will not be the same story if I have a closed interval. So, I will just show you this fact. So, there is a huge paradigm shift if you move from an open interval to a closed interval. Suppose if you take the minimum, want to find the minimum value of f x equal to x square, y equal to x square over x belonging to the interval 1, 2. You very well know that we can draw the graph of this, y equal to x square. So, from 1 and this is 2. So, at 1 so this is 1 and this is 2, 1 the value is 1 and 2 the value is 4. So, you know over 1 2 the minimum value is obtained at 1, x equal to 1 is the minimum value. So, in this case x star is the global minima is 1, but what is f dash x star? F dash x star is 2 because it is 2x and you put 2x star, and if you put x star equal to 1, so when x star is 1 and f of x star is 2 and it is not equal to 0. So, whatever you know for this and the whole real line and open interval does not hold true when you are in the setting of a closed interval. And so, in that case you have to think about something else. We will come into that later because we have a separate section on optimization where we will think about this. But now what about the sufficient condition? We will come to this later, but here I want to tell you about some important fact which is usually never told in a calculus course, but this is something you should realize at the very beginning, and then your understanding of, as I told you, of calculus would be much better. Now here we are talking about local minimum, local maximum and all those things, but here I will give you an example where the global maximum of a problem can look like a local minimum. So, this is a very standard result, and this proof this function I have taken from the book of Fletcher. It is one of the most well known, it is called the Wizard of Optimization. The name of the book is Practical Optimization, published by Wiley. Here he gives a very interesting example. He says consider the example phi x, which is minimum of 1 plus x, 0, 1 minus x. So, what does it mean? So, you plug in an x and compute all these 3 different functions, and whatever is the minimum value among them, that you return as the value of the function phi x. Now, what does y equal to 1 plus x represent? It represents the line x minus y equal to 1. And what does y equal to 1 minus x represent? It represents the line x plus y equal to 1, and y equal to 0 represents the x axis. Sorry, it is y minus x is equal to 1. So, if you draw the graph, let us first draw the graph. So, you know this y minus x and x, these 2 lines would meet at 0 1, they will both pass through 0 1, because when x is 0, in both cases y is 1, and when x is 1, for example, when right. So, for example, when y is 0 here, in this case x is 1, and when y is 0 here, x is minus 1. So, this represents the line y minus x equal to 1. So, minus 1 0, and then this goes through 1 0, and this is my x equal to 0. So, take any point here. So, what is the minimum value? The minimum value between these 3 minimum. So, if I evaluate this functional value, so this line is going like this, this line is going like this. So, the minimum value between these 3, this y axis 0, x equal to 0, this and this is the number here. So, up to minus 1 0, this is the minimum value, and after that between minus 1 to plus 1, 0 is the minimum value, because both are above 0. Again after 1 0, this is the minimum value. So, if you now look at the function carefully, the function is this minus 1 0 0 1. So, this is 0 1, something like that. Sorry. So, this is 1 0. So, that this looks like an inverted tub. So, look at this point x equal to 0. So, x star equal to 0. So, I will take a very small delta neighborhood around it, so that delta neighborhood completely remains within this line minus 1, line joining minus 1 plus 1. So, this is my delta and this is my minus delta. Okay? That is what it does. Okay. Now, I want to tell you something very interesting here. Now, for whatever y I take in this interval, for all y element of minus delta to plus delta, what do I have? I have f of y is equal to 0, which is equal to f of x star, which is f0, where x star is 0. So, hence it satisfies the definition of my local minimum over of the function over x equal to r. But is the point x star equal to 0 really a local minimum? What is the real property of this point? It is a global maximum of the function, because the function value, all the function values are either negative or 0. So, here, just this definition is unable to really distinguish the situation where a global maximum can be misinterpreted as a local minimizer, because at this point also f dash x star equal to 0, right. So, in that case one defines what is called a strict global minimizer or strict. So, there is a concept of strictness coming in. So, how do you define a strict global minimizer? I will just write that definition and will then. So, I am writing everything for minimum because I am more comfortable with it. Everybody does what he or she is comfortable with it, but I would like you to also try out the things for the maximum. Those who are students from economics would like to try out the maximum yourselves, because that is what you would require. Now, so strict local minimum. So, what does it mean? X star is a strict local minimum of f over a if there exists delta greater than 0 such that for all x element of a intersection x minus delta x plus delta and x not equal to x star, we must have f of x strictly bigger than f of x star. This is the key idea. For example, if you take x equal to 0 for a y equal to x square, this is a strict global minima in fact, because if you take any, go to any point in on the right side or left side, the function value is strictly 0. There is no other point on R for which x square is 0 other than 0. So, that is, so 0 is a strict local minima. So, the strict local minima is something important that takes away this sort of very strange looking points out of your discussion. So, now once I have got f dash x equal to 0, that does not immediately tell me whether that is a maximum or a minimum. For example, if I take the function f x equal to x cube, and I draw the graph of this, that I had been advising from the very beginning, or rather advocating that you should try to draw graphs of functions, because that makes their nature very clear. Because now you have mathematical packages for, and those who have access to it can use those mathematical packages. Now, if you compute f dash x star equal to 0, so you will get 3 x star square equal to 0, which will imply that the only solution that you have is x star equal to 0. But look at x star equal to 0, the function values on the right side is bigger than it, function values on the left side is smaller than it. So, it is neither maximum or a minimum, local global does not matter. So, f star x star equal to 0 does not say anything about the true nature of the problem. If x star was really a minimizer, it would have satisfied this definitely. So, I have computed out a point which is satisfying this. So, usually any point for which f star x star equal to 0 is called a critical point. Now, what I want to tell you is that there is a difference between a critical point and a minimizer. Here x star equal to 0 is a critical point, but it is not a minimizer or maximizer in case of x cube. So, what additional information you need, that okay, if I find an point x star such that f star x star equal to 0, the only thing that I can tell about that point, that it is the critical point of the function or a stationary point, according to physicists like to call it a stationary point. If I have that point, there is no way I can say that that is a minimizer. So, there must be some additional conditions required, and for that conditions I need f to be twice continuously differentiable. So, let f from R to R be twice continuously differentiable. Let x star be a point, let x star be a critical point and that is f dash x star equal to 0, then and f double dash of x star is strictly greater than 0, then x star is a strict local minimizer. This is a statement which is never given in any calculus classes. This is something important. This is the true nature of the local minima that you get. If you put this additional condition, you get a strict local minimizer, you just do not get a local minimizer, you have that additional stronger thing coming to you. It is a free gift actually. So, where is the proof that this would happen? So, for the proof we have to wait for one more class that okay, such things that this would actually give me a strict local minimizer. So, this is the basic idea of unconstant optimization. So, when we will study there is a section class on optimization, then we will look into the issue what would happen when you would have constraint situation like the one that we have given. How do we select out points there? So, that would be given in a separate lecture where we will, because this whole issue of maxima minima is very important and it has huge applications. So, that is something we will really do. So, with this I would really like to stop my class. I hope you have a very basic idea of maxima, minima and maxima. Maxima you can figure out yourself how to write the same old story for whatever I have written. The story that I wrote down for minimization, the same story works for maximization, but you have to write it down in a proper way. In this case you would have strictly less than 0, then you will have a strict local maximizer. So, you can define things like that also. So, with this I end this class and hoping that you are actually progressing well in understanding. Any problem you can write to the forum and we will answer you back. My TAs would answer you back, and please feel free to ask a question. Please note that no question is stupid enough that it can't be asked. Of course, do not ask us what is your name sort of thing, ask us some question which is relevant to this courses and lecture. If you have some criticism about the lecture, you want the lecture to have some component, please let us know. And also I would like to assert once again that the philosophy of this course is not really to make you prepare for some examination, because you will never learn things by preparing for examinations. You only learn the concepts really when you are free in your mind and concentrate on learning the concept. So, our whole questions would be actually conceptual based, it is based on the very basic concepts. We will in the tests and examinations for those who would give, we would test the basics. We are not going to ask you very complicated question where you have to do strange maneuvers. By doing very complicated mathematical computation does not tell you that you have a very great mathematical mind. Mathematical minds are ones who works more on the concepts. Thank you very much.